How to make solar panels from algae. Solar panels made from algae, often referred to as algal biophotovoltaics, BPV, are an emerging concept in the realm of renewable energy. This approach leverages the photosynthetic properties of algae to produce electricity. Algal BPV systems use living organisms like microalgae or cyanobacteria to convert sunlight into energy. Here's a basic overview of how this can be done. Materials needed. Algae/cyanobacteria, specific strains of algae, such as Chlamydomonas reinhardtii or Synechocystis, are often used due to their efficient photosynthetic capabilities. Transparent substrate, glass or clear plastic to allow sunlight to reach the algae. Electrodes, conductive materials, like gold, platinum, or carbon-based electrodes, are used to capture and transfer the electrons produced by the algae during photosynthesis. Growth medium, nutrient solution for algae, typically water with nutrients like nitrogen and phosphorus. Conductive layer, indium tin oxide, ITO, or fluorine-doped tin oxide, FTO, is commonly used to form a transparent conductive layer. Light source, natural sunlight or artificial lighting, like LEDs, to simulate sunlight. Steps to make solar panels from algae. Culture the algae. Start by culturing algae in a suitable growth medium, like water with nutrients. Algae need sunlight, carbon dioxide, and nutrients to grow and thrive. Culturing algae can be done in photobioreactors, which are closed systems that allow the controlled growth of algae using light and CO2. Prepare the electrodes. Select conductive electrodes, e.g., gold or carbon-based materials, that will serve as the points for harvesting the electrons produced by the algae. Coat these electrodes with a conductive material such as ITO or FTO, ensuring transparency for light to reach the algae. Immobilize the algae. The algae are usually immobilized on the surface of the conductive electrode in a thin, even layer. This can be done by either allowing the algae to naturally attach to the surface or by using a gel matrix, e.g., agar, to trap the algae on the surface. Create a circuit. Connect the electrodes to an external circuit. During photosynthesis, algae generate electrons that can be transferred to the conductive surface. These electrons are then harvested via the electrode, which is connected to a circuit to capture the energy. Power generation. When exposed to light, the algae undergo photosynthesis, producing electrons. These electrons are passed onto the conductive surface, electrode, and can be harvested to generate electricity. The efficiency of these systems is relatively low compared to traditional solar panels, but ongoing research aims to improve the yield. Maintain the system. Regularly feed the algae with nutrients and CO2 to ensure continued energy production. Algal cells eventually die, so replenishing or refreshing the algal culture is necessary over time. Challenges and considerations. Efficiency. Current algal biophotovoltaic systems have relatively low efficiency compared to conventional silicon-based solar cells. Enhancing the electron transfer process and improving the interface between the algae and electrodes are active areas of research. Maintenance. Algae require constant care, such as exposure to light and the right balance of nutrients. Maintaining a live culture can be more complex than handling static solar cells. Scaling. While lab-scale systems exist, scaling up to commercial viability is still a challenge. Sustainability. Using algae for solar power is highly sustainable due to its abundance, ability to grow in non-arable land, and minimal environmental impact. This technology is still experimental and not widely available commercially, but it represents a promising avenue for sustainable and eco-friendly energy solutions in the future. How to optimize this system? Optimizing an algae-based solar panel, or biophotovoltaic, BPV, system, involves addressing several technical and biological challenges to enhance efficiency, longevity, and scalability. Below are key strategies and research areas for optimizing the system. 1. Enhancing electron transfer efficiency. Improve electrode materials, use more conductive and biologically compatible materials for electrodes to facilitate better electron capture. Materials like carbon nanotubes, graphene, or metal organic frameworks, MOFs, can improve the conductivity in surface area for electron transfer. Surface functionalization, functionalizing the electrode surface with biocompatible polymers or nanoparticles can enhance the binding between algae and the electrode, improving the transfer of electrons from algae to the electrodes. Optimize electrode spacing, design the electrode configuration to minimize the distance electrons must travel from algae to the electrode. Thin film electrodes and precise layering can reduce resistive losses. 2. Improving photosynthetic efficiency. Genetic engineering, genetically modify algae strains to enhance their photosynthetic efficiency and increase electron production. For example, reducing the energy losses in the Calvin cycle, improving light absorption across a broader spectrum, or enhancing the rate of electron flow during photosynthesis are active areas of research. Artificial photosynthetic boosters use molecules like dyes, quantum dots, or nanomaterials that can absorb sunlight and transfer energy to algae, thereby boosting photosynthetic activity and electron production. Light-optimized algae cultivation, ensure that the algae are exposed to optimal light conditions. Light intensity, wavelength, and duration should be adjusted based on the algae strain being used. Incorporating light-concentrating lenses or reflective surfaces to direct more sunlight to the algae layer can increase photosynthesis efficiency. 3. Maximizing algal growth and productivity. Photobioreactor design, design efficient photobioreactors, PBRs, to maximize the exposure of algae to sunlight while ensuring a steady supply of CO2 and nutrients. These reactors can include features like mixing systems to ensure that all cells get sufficient light, and bubble columns to enhance gas exchange. Nutrient optimization, ensure an optimal and continuous supply of nutrients like nitrogen and phosphorus to promote sustained algal growth. Using sensors and automation for nutrient delivery can reduce the risk of overfeeding or underfeeding, which may affect both growth and energy output. Optimize CO2 supply. Efficient CO2 feeding is crucial for enhancing algal photosynthesis. Consider integrating CO2 from waste streams, e.g., from industrial processes or fermentation, to improve sustainability and boost algal productivity. 4. Minimizing energy losses. Minimize ohmic losses, reduce resistance in the circuit by using high-quality conductive materials and optimizing connections between the electrodes and external circuit. Reduce respiration losses, algae undergo respiration in the dark, which consumes some of the electrons they produce. To minimize this, consider strategies like separating photosynthetic stages from respiration phases through light-dark cycling or using metabolic inhibitors during dark periods to suppress respiration. Optimize algal layer thickness. Algal films need to be thin enough to allow light to penetrate, but thick enough to produce significant energy. The optimal thickness can be identified through trial and error or simulation models based on the algae strain and light source. 5. Scaling and designing modular systems. Modular system design, design systems in a modular fashion so that individual units, biophotovoltaic cells, can be scaled up easily. Modular designs allow for repair, replacement, and expansion with minimal disruption. System integration. Explore ways to integrate BPV systems with existing infrastructure, like using algae panels in green buildings as part of walls, roofs, or windows to generate electricity and filter air. Reduce water usage. Implement a closed-loop water circulation system to reduce water consumption. Algae grow in water, so managing water resources efficiently is critical, especially in arid regions. 6. Long-term stability and maintenance. Biofilm management. Over time, algal biofilms can form on surfaces and reduce efficiency. Incorporate self-cleaning surfaces or mechanical cleaning systems to prevent biofouling and maintain efficiency. Culture longevity. Ensure that the algae culture is long-lived and robust by monitoring growth conditions, light, temperature, pH, and nutrients, and periodically replacing old cultures with fresh algae to maintain productivity. Encapsulation technology. Encapsulating algae in hydrogel matrices or nanomaterials can help to stabilize the algae and improve their lifespan while allowing nutrients and light to reach them efficiently. 7. Hybrid systems. Integrate with traditional solar panels. Hybrid systems that combine algal biophotovoltaics with traditional silicon-based solar cells can harness both algae's photosynthetic power and the photovoltaic effect of standard solar panels, enhancing the total energy output. Dual-use systems. Use algae systems to simultaneously produce biofuels, such as algae-derived biodiesel, or valuable byproducts, such as biomass for fertilizers or pharmaceuticals, while generating electricity. 8. Artificial lighting for controlled environments. In places where natural sunlight is insufficient, controlled artificial lighting like LEDs optimized for photosynthesis, using the right wavelengths, can help maintain consistent productivity, especially in indoor or urban settings. 9. Optimizing the power output. Voltage matching. BPV systems typically generate very low voltages. Employ voltage-boosting circuits like DC-DC converters to enhance the power output to levels that are more useful for powering external devices. Energy storage. Integrate energy storage systems like batteries or supercapacitors to store the energy generated, allowing it to be used when sunlight or algae productivity is low, e.g., at night. 10. Collaboration with AI and machine learning. Use AI and machine learning models to optimize the operation of the BPV system by analyzing large datasets from sensors monitoring light intensity, temperature, pH, and other factors. AI can recommend adjustments in real time to enhance performance and efficiency. Conclusion. Optimizing algae-based solar panels requires a multifaceted approach involving improvements in both the biological, algae, and technological, materials, design, aspects. Advancements in electrode materials, genetic engineering, and system design, along with hybrid and modular approaches, will play crucial roles in enhancing the overall efficiency and scalability of this promising renewable energy technology.